What I want to talk about now is a tool for measuring how fast things in space are moving. You might think, well, can't you just look at something and see how fast it's moving? It's not always that easy when the thing you are looking at is really, really big and it is very, very far away and the motion may be slow. At least the apparent motion may be slow. This is a galaxy. This is the Andromeda Galaxy. Galaxies rotate as their stars orbit around the center. A galaxy the size of the Andromeda Galaxy, a star on the outskirts of the galaxy, might take 250, 300 million years to go around the galaxy once, which means we would have to watch a star on the edge of the galaxy for 1 million years just to see it go 1/100th of the way around the galaxy. We are obviously not measuring the speed of rotation of galaxies just by looking at the stars and watching them move. They don't move enough for us to see that. But luckily, just like we saw with blackbody radiation and with spectroscopy, light carries information about the motion of its source that we can figure out if we are clever. This physical effect is called the Doppler effect or the Doppler shift, and it's something that we are all familiar with sound. If you have an object that's giving off waves, like the siren on an ambulance giving out sound waves, and that object is sitting still, then that object gives out sound waves in all directions with the same wavelength and the same frequency. And if you were standing in front of the ambulance or behind the ambulance, the sound will be the same. But if you are standing by while this ambulance moves past you, as it moves, it is catching up with the sound waves in front of it, causing them to arrive at your location with a higher frequency. And if you are behind it, the ambulance is moving away from its own sound waves, stretching them out and causing them to arrive at your location with a lower frequency. We can hear this shift with our ears. We're familiar with the sound of a passing car engine as it drives past going meow. And it changes in volume, but also changes in pitch. High pitch as it approaches us, low pitch as it moves away from us. I mentioned, I think, in the video about the human ear that the human ear is very sensitive to small shifts in frequency. We can hear the Doppler shift with our ears, even if the object emitting the sound waves is not moving very fast. I could hear it when the Mr. Softee ice cream truck drove through the neighborhood playing its little Mr. Softee song. Even though an ice cream truck only goes about 30 miles an hour, as it moved away, because your ear is very sensitive to small changes in pitch, I could hear the little song getting flat as the ice cream truck moved away. So the Doppler shift for sound is very familiar and very easy to measure. Now, for light, the Doppler effect also happens, but it is not as easy to observe or measure because not many things around us go a substantial fraction of the speed of light. It is easy to catch up with your own sound waves because sound only moves a few hundred feet per second. It is not easy to catch up with your own light waves because light moves hundreds of thousands of miles every second. So in order for something to have a Doppler shift of its light that you could see, it would have to be going 5%, 10% the speed of light. But the same thing happens. As an object gives off light waves, it catches up with the light waves in front of it, causing the wavelength to be squished, causing the frequency to be higher, causing that light to be bluer. So an object approaching you, the light that that object is emitting will be shifted towards the blue end of the spectrum. As it moves away from you, it is moving away from those waves, it is stretching them out, causing them to arrive at your location with a lower frequency, and that causes a red shift. The spectral lines are shifted towards the red end of the spectrum, and if this rocket ship were white, as it approached you, that rocket would look bluish, and as it moved away from you, it would look reddish. Nothing around us moves fast enough that we could see this with our eyes. In order to detect the Doppler shift for light, we need either something needs to be moving very, very, very fast, or we need very, very sensitive electronic equipment that can measure this frequency very accurately. If you've ever gotten a speeding ticket from a police officer with a radar gun, how does that device work? It emits radio waves. Those radio waves bounce off the front of your car. And if your car is moving towards the police officer, when they bounce off, their frequency is blue shifted. That electronic device is sensitive enough to measure that tiny frequency shift, and it can tell how fast your car is going. I will not bore you with the equation for the Doppler shift, but the shift in frequency is proportional to the velocity relative to the wave. So the relative speed between the rocket and the speed of light, however fast that is, that's the relative shift in the frequency. So all we have to do is measure the frequency shift, and we can measure how fast that is going. How do we actually measure how fast the Andromeda Galaxy is rotating? Well, if it's rotating, that means one side is moving towards us and the other side is moving away from us. So if it's rotating, that means the spectral lines of all the stars on one side of the galaxy will be slightly blue shifted because that side of the galaxy is moving towards you, and the spectral lines of all the stars on the other side of the galaxy will be red shifted because those stars are moving somewhat away from you. So by comparing the spectral lines of one side of the galaxy and the other side of the galaxy, measuring the blue shift of those spectral lines and the red shift of these spectral lines, we can determine how fast the galaxy is rotating. This is also how we discovered the expansion of the universe that is described by the modern Big Bang theory. When we look at nearby galaxies and we look at faraway galaxies, we notice that their spectral lines, the spectral lines of, it's mostly hydrogen. 90% of the atoms in the universe are hydrogen atoms. We notice that the hydrogen spectral lines in the nearby galaxy are red shifted by a little bit. But the spectral lines in the distant galaxy are red shifted by more. Meaning the nearby galaxy is moving away from us, but the very far away galaxy is moving away from us faster. And this picture of galaxies all moving away from one another faster and faster the further apart they get is the raw data that led us to postulate the idea of the expanding universe. It is the primary observation that gave rise to the Big Bang model of the expanding universe. The fact that all of the galaxies in the universe, except the ones in our local group, all of the distant galaxies in our universe are moving away from us. And the way we know that is by observing the redshift of their spectrum. So if we want to know how fast something is moving, all we have to do is measure its Doppler shift, if it's moving towards us or away from us. If it's moving this way, it's a little more complicated. There is something called the Transverse Doppler Effect, but it's way smaller and way harder to measure. The Doppler Effect is mostly useful for line of sight velocity, things either moving towards you, blue shifted, or away from you, red shifted.